Okay, let's look at the general procedure for solving absolute value inequalities. And I've listed the procedure above, and I'm just going to do it by an example here. So we're looking at an example: 1/3 open absolute value 3 minus x, closed absolute value is less than or equal to 2. Alright, so first step is to isolate the absolute value. Notice that I need to get rid of this 1/3 in order to isolate the absolute value. To do that, I'll multiply both sides by 3. So I have open absolute value 3 minus x, close absolute value is less than or equal to 6. There, now my absolute value is isolated. I'm at step 2, and I have two potential things that could happen. Either my absolute value is going to be less than some number, or my absolute value is going to be greater than some number. In this case, it's less than, so I'm in step A. And step A says that it should be, okay, whatever's inside the absolute value, less than the number. So essentially just rewriting this statement without the absolute value. So 3 minus x is less than or equal to 6. Okay, just rewrote it without the absolute value statement. And so notice in this step, when it's less than, it's and the way we remember that is less than and it just kind of sounds nice together, right? And whatever's in here is greater than negative that number. So 3 minus x, switch the inequality to greater than or equal to, and then change the sign of this number, -6. And if you saw when I introduced the solving absolute value inequalities, there is a reasoning behind doing this. You don't have to memorize this procedure. You can just think, okay, I need this distance to be less than 6 from 0. So that means that whatever this number is has to be less than or equal to 6 and greater than or equal to -6. Then you can go back to that video if you need a refresher. Okay, so we've satisfied this. We set up the 2. Let's solve both the inequalities. So here I'm going to subtract 3 from both sides, and I have -x is less than or equal to. By subtracting 3, I'm left with 3. Now, well, this is a -1 times x is less than or equal to -3, so I'm going to divide both sides by -1, and I have x, instead of being less than or equal to, is going to be greater than or equal to -3. Remember from Algebra 1, when we divide or multiply both sides of an inequality by a negative, we must flip the inequality symbol. Okay, so let's look at the other side. We're going to do exactly the same thing. I have -x is greater than or equal to, I have to subtract 3 from both sides. This amounts to -6 minus 3, which is -9. Now I'm going to divide by -1 again and switch my inequality because I'm dividing by a negative. X is less than or equal to +9. Now remember, this is an AND statement, so the final result can be written as a compound inequality. X is greater than -3 is the same thing as -3 is less than or equal to x. And I correct myself here. I should have said x is greater than or equal to -3 is the same thing as -3 is less than or equal to x. Also, since and then we can just finish up and put this in here, x is less than or equal to +9. Okay, and that's a nice compound inequality. That is displaying using the set builder notation. That's the extent we're going to delve into set builder notation for now. Okay, now graphical representation. X is greater than -3, greater than or equal to -3, which is right here. X is greater than or equal to -3. Going this way, that's the numbers greater than or equal to -3, -2, -1, 0, 1, 2, 3. And x is less than or equal to 9. So here's 9, less than or equal to 9 is to the left. So we're just going to connect this. And we're just saying all the numbers between -3 and 9, including -3 and 9, are solutions to this inequality. Now, when we go to verify our answer, the way we're going to do it is we're going to verify the endpoints, the -3 and the 9. So for instance, I'm going to plug in 9. 9 should be the largest number I can plug into here, such that the number will still be less than or equal to 2. In fact, when I plug in 9, I should get 2. And if I plug in a number greater than 9, I should get a number greater than 2. So let's verify that. That's what this boundary means. So I'm going to plug in 9. So I have 1/3 absolute value 3 minus 9 closed absolute value is less than or equal to 2. Well, I have 1/3 open absolute value 3 minus 9 is -6, closed absolute value is less than or equal to 2. Remember, these are question marks, so that's hopefully this is true. This is us verifying the solution. Absolute value of negative 6 is 6, so I have 1/3 of 6 is question mark less than or equal to 2, and of course 1/3 of 6 is 2. So that worked out. Now notice, if I had picked a number greater than 9, if I picked a number like 10, 3 minus 10 would have given me negative 7. And that would have amounted to being positive 7 here, and 7/3 is in fact greater than 2, so it would not have worked. So no number greater than 9 would work. And you can do the same thing for negative 3. In fact, we're going to do that. Let's look at what happens when negative 3 should be the smallest number I can plug into this inequality, and it still be less than or equal to 2. And if I plug in a number like negative 4, it should be greater than 2. So let's check that. We have 1/3 of open absolute value, 3 minus negative 3, closed absolute value is less than or equal to 2. So this is 1/3 of absolute value. 3 minus negative 3 is 3 plus 3, which is 6. Is less absolute value of which is of course 6. So I'm at the same stage I was before. 1/3 times 6 is 2. This is 2 is less than or equal to 2, which is exactly what we wanted. And notice
if we picked a smaller number,
-4, it would have been 3 plus 4, which would have been 7, which would have put us in the exact same spot we were in before. So these boundary conditions are the boundaries of the solutions, and if you go beyond them, you will not have a solution that satisfies this inequality.